My name is Zihao, and during the summer of 2017, I worked with my advisor, Johanna Hardin, on this project called Bag of Little Bootstraps. To get started, I would like to give an overview of our project. So the goal of our project was to build and implement an efficient machine learning algorithm called Bag of Little Bootstraps. And the approach we took was that we first built the theoretical foundation of this algorithm using the standard rainforest and Bag of Little Bootstraps method. And then we implement our method in the language R. And finally, we tested the statistical and computational performance of this algorithm. And the motivation behind this project was that rainforest is a very robust machine learning algorithm in classification and regression settings, but it suffers from several drawbacks. The first main 2 points are that rainforest uses a lot of time and memory consumptions, and these are important factors that machine learning practitioners consider in their actual work. And also, rainforest is not well adapted to parallel processing, which means that we cannot use the power of multiprocessing of multiple cores on your modern computers. And furthermore, when the dataset is really large, rainforest is unable to load the dataset into the memory and thus could not make any reasonable predictions. So that's why we want to build this new machine learning model called Bag of Little Rainforest. And we aim to reduce the time and memory consumptions while designing this algorithm that has a structure that is that allows for easy parallelization of sub-calculations. And finally, we'll want our model to be able to deal with big datasets, which is prevalent these days. To give people a brief overview of supervised machine learning, so the general workflow of supervised machine learning is basically when you have a training dataset and you want to build this model that is able to make reasonable predictions based on new data. So if you have learned about linear regression or logistic regression, these are both examples of supervised machine learning. And there are 2 broad categories of supervised machine learning. First one is classification, and that's when you have a set of feature X and you're trying to predict something discrete, such as cat versus dog. And the second problem is called regression. That's when you have a set of features X and you're trying to predict something that's continuous. So on this plot, you can see that we're trying to predict the Y coordinates of each of the points using the X values. So to talk about our algorithm, we need to talk about 2 of its building blocks, rainforest and Bag of Little Bootstraps. So to start talking about rainforest, we need to start from what's called a decision tree. So decision tree in a regression setting. So decision tree is a tree that's constructed by recursively partitioning the training observations into a number of regions. And we call these regions R1 to Rj. And these regions are constructed such that they represent the most homogeneous spaces with respect to the responsible variable of the data. So essentially what that means is that we're trying to break down the data into small groups where the data points are close to each other in terms of their Y values. So this is an example of a trained regression tree. And the problem we're dealing here is we're trying to use the price and type of vehicles to predict their miles per gallon. So assume that we have this new training data point. This regression tree will answer a series of questions where if the answer is yes, we'll go to the left branch of the tree, and if the answer is no, we'll go to the right branch of the tree. So faced with this new data point that has price of 10,000 and type of vehicle equal to large, the decision tree will go to the left branch for 3 times, and then finally end up in this node, which means that the prediction for this new observation will be 19. And to give people a simpler, more intuitive example, assume that we have 1,000 observations. Each data point has 2 features, x1, x2, and one response variable or label y. And 250 of these observations have y value equal to 5, while 750 of them have y value equal to 10. So we start by plotting all of these data points on a plot, and we can see that the data points that have y value equal to 5 are in green, while the rest are in red. And furthermore, to build this decision tree, the tree will first go through each of the possible cutting points of the x1 and x2 values. And it might find that, oh, this might be a good cut of the data points because it separates the data point into two regions, where the top region is completely homogeneous with respect to the y value, but the top part is not. So that's why it'll go through another binary split of the data points. And finally, we'll just end up with 3 different regions where all of the data points are homogeneous to each other with respect to their y value. Sorry. But again, this is an oversimplified example. In the real world, we can't get this perfect data. And a decision trees also suffers from high variability. Because if we give it a slightly different training sample, the tree trained will be very, very different to each other. So that's why random forest includes a second step called bootstrapping. So essentially, bootstrapping is when we have a sample of size capital N, and we repeatedly sample n observations with replacement from the sample to form resamples. Essentially, graphically, so assume that we have this sample of size n to start with, and we repeatedly sample with the replacement from this sample to get our resamples. Because we're doing sample with the replacement, that means for each of the resamples, we can see repeats. So you can see a lot of these blue points occurring for multiple times and black dots occurring for multiple times, whereas in the original sample, there's only one black dot. And it turns out that we can use this kind of idea to train a different decision tree on each of the subsamples we obtain. So we can already see that using each of the resamples, because each of the resamples are slightly different, that's why we can build different decision trees. And with this set of trees, we can already get a sense that if we group a lot of trees together, it forms a forest. So more theoretically, random forest is a collection of decision trees that satisfies 2 conditions. First is that each tree is built using a resample of size n drawn from the training data. And that is to say that that is a direct parallel between what we just saw in the previous slide about the bootstrapping method. And the second criteria is that each binary split for a tree uses only a subset of all of the input features. And that says, again, going back to one of our, sorry, can everyone hear me all right? Is there a problem at all? Okay. The second criteria is that, so essentially each of the trees is building only a subset of all of the input features, so that each of the trees are decorrelated and different from one another. So the combined effect of random forest is such that we can build a set of very different decision trees so as to minimize the variability of each of the trees and make our predictions more robust. And now we're ready to talk about Bag of Little Bootstraps, which is a standalone different method than random forest. Is a resampling method. And we need to start by talking about what's called subsampling. So essentially, subsampling is the process of partitioning the data into subsets with no overlapping elements. And there are two important points that we need to realize for the subsampling process, which is that first, with sufficient number of cuts, each subsample is much smaller than the entire sample. And second point is that resamples can have repeats because essentially we're sampling with replacements. But subsamples are not overlapping and distinct. And that means each of the observations within the subsamples cannot belong to two different subsamples, and they are all individual distinct observations. And now we're ready to talk about BLB. So BLB starts with a training data set of size n, and it begins by subsampling the observations into S subsets of size B. And then within each subsample, we resample up to size n for multiple times. This step is a little bit confusing, but I'll be illustrating it using a plot right below. And one point to notice is that we are resampling up to size n, which means that each of the resamples has the same size of the original training data. And then we do something with each of the resamples, such as building a model. And finally, we average the results within each subsample, and then finally, we aggregate all of the results from all of the subsamples. Again, to illustrate step number 2, assume that we have this subsample of size 5, and we have 5 distinct observations, and we're trying to resample up to size capital N equal to 100. So we repeatedly draw from this subsample with the replacement. That's why you can see all of the points appearing for multiple times. And there are two main benefits of the BLB method. First one is that calculation on each subsample can run in parallel, and that is a great thing for a modern algorithm, because each of the laptops nowadays has at least 4 cores. So when a algorithm can use parallel processing, we can speed up the computation by a lot. And then the second benefit is that now big data sets can be loaded using the subsampling process. Recall that each subsample is much smaller than the original training sample, so we can imagine that we can load in the big data sets sequentially by using the subsampling process or using a bunch of subsamples at a time. And graphically speaking, BLB starts with input data of size n. It starts by partitioning the data into subsamples, where within each subsample we do resample and build a model. And we aggregate the results within each subsample to get its prediction. And finally, we do model ensemble. It turns out that random forest and Bag of Little Bootstraps can be beautifully combined into this new machine learning algorithm called Bag of Little Random Forests. Essentially, BLRF starts again with a data set of size n. It subsamples the observations into S subsamples of size B. And then using each subsample, we build what's called a little random forest by repeatedly drawing resamples of size n to build n-tree number of decision trees. And finally, we average the predictions within each little random forest to form its predictions. And finally, the entire algorithm averages the predictions from all of the little random forests. Again, graphically speaking, we start with this input data of size n. We partition the data into subsamples. We perform resample within each of the subsamples to form decision trees. And then we combine all of the decision trees to form little random forests. And finally, we combine all of the little random forests as a bag of little random forests. And that's where the name comes from. And to test out our algorithm on data, we performed a simulated study on three different kind of data structures, and those are linear, cosine, and clustered. And notice that each of the axes here are drawn from the uniform distribution from 0 to 1, and each of the epsilons are standard normal from with mean equal to 0 and standard deviation equal to 1. And for hardware, we used what's a machine called Outlier that has 64 CPUs to allow for multi-processing. And some experimental results. we compute the relative performance of our algorithm over the standard random forest. One big takeaway from this plot is that the larger the subsample, the lower the relative performance, which means our model is performing better. And the more number of little random forest, the better the algorithm is. But number of trees within each little random forest doesn't matter that much. And again, a comparison between our algorithm and the little random forest, you can see that asymptotically, our algorithm does about the same as the standard random forest. But in here, you can achieve for about 20% of time save. And empirically, these are the the optimal values for each of the tuning parameters for our algorithm. And again, we can parallelize this process so we can speed up the computation by a lot. Some further directions include expand to classification setting and consider OOB errors. And we can also build our algorithm on top of a more optimized package called Ranger. These are the list of references, and thank you very much. Thank you for your time.
Thank you so much for that presentation. We'd like to remind anyone listening that if you have any questions, feel free to type them into the chat box. So first, to start off, we have a question from Nicole Pereira, which is, what was the most challenging part in your research and how did you overcome that challenge?
Yeah, the most challenging part of my project was that prior going into this research project, I had no experience coding, especially in the language C, because the standard random forest was built in the language C. I had to learn this language from ground up, and after learning this language, I had to adapt this new machine learning method in this new language. And but along the way, I feel like I learned a lot about how to build an R package, how to use what I just learned within several weeks to build a completely new thing. And yeah, that through that process, I learned a lot.
Yeah, that's very impressive. We have another question from Michael Posner, which is there a recommendation on the minimum sample size per subsample in addition to number of subsamples?
Yeah, so going back to the slide, each of the subsamples has to be at least 15% of the original sample to obtain a reasonable prediction. So assume that we have a very small subsamples, even though that the computation could be really fast, but because each of the subsamples are only exposed to a very small subset of all of your data, it cannot generalize well to unseen data. And in reality, if you have like 10,000 observations, you will want to have at least like 1,500 or like 2,000 observations.
Right, thank you. Another question we have is, how did you get interested in this project?
So before this summer, I approached Professor Hardin, and because I was really interested in algorithmic design, and this was actually another senior thesis done by another student, and I read over her senior thesis and thought that this is a topic that I was really interested in, and because I performed relatively well in my math classes, and Professor Hardin just wanted me to build this algorithm. And the theoretical foundation was pretty much laid out. And the more difficult part was to actually implement this algorithm in R and do some simulation studies on it.